All right, strap in, guys, because this is the dreaded question number 6 on the BC calculus free response question, which is ordinarily the series question, as you can see right here. The Maclaurin series for a function f is given by this summation, blah, 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 and converges to f of x for all x in the interval of convergence. It can be shown that the Maclaurin series for f has a radius of convergence of 6. That's interesting. They just straight up gave us that radius of convergence. So it basically looks like this. That realize it's Maclaurin, which means it's centered at 0. So you have the absolute value of x is going to be less than 6, which would, in terms of like an algebraic solution, imply that your interval is between -6 and +6. Now, we know what the radius of convergence is, but we don't know if this is exactly the interval of convergence because it could include or exclude the two endpoints. And the reason why you'd have to be able to check them is because this is ordinarily gotten with the ratio test. Ratio test would basically equal 0 on both of these, not 0, sorry, 1 on both of these endpoints, which is inconclusive. So you usually have to test the endpoints. Anyway, let's look at A. Determine whether the Maclaurin series for f converges or diverges at x is equal to 6. Well, take a look at that. It's basically wanting us to test this endpoint over here and give a reason for your answer. So if we're having to give a reason for convergence or divergence, it's basically using one of our convergence tests. So I'm going to need some room for this. So I made some room, as you can see. Determine so I basically need to evaluate f of 6 so I can see what this series looks like. So f of 6 is equal to summation n equals 1. That is weird. It's starting at 1 instead of 0. Now, the variable here is x. So f of 6 is only affecting the x here. None of the n's get affected because the n's are controlled by the summation here. So n plus 1 stays, but this x becomes a 6 to the n over n squared 6 to the n. Look at that. Get out your cancellation crayon because these things go away. And this is going to reduce to the sum n equals 1 to infinity, just like before, n plus 1 over just n squared. There you go. And we're trying to see, does this converge or diverge? Squint down. Take a look at the dominant terms here. This looks like it's trying to be the harmonic series in disguise. Harmonic. And what does the harmonic series do? It diverges. So now this right here is not enough justification. We have to actually use an appropriate test and make sure that we have fulfilled the criteria for that test and so on. So what test can we use to show that this one diverges since the harmonic series diverges and it's so closely related? You can't use the ratio test first of all. The reason why you can't is because this is P series. This is very close to P series, and ratio tests and P series do not cooperate. You would just get a common ratio of 1, which is inconclusive for the ratio test. So use something else. And with these kind of series, there's really two options. You've got either the comparison test or the limit comparison test. And let's just see if we can make the comparison test work. To use the comparison test, our series has to be bigger than a divergent. I'm just going to write that down real quick. Bigger than divergent. And that's, in a nutshell, layman's terms for what the comparison test is trying to show. So if we can't make that inequality happen, in other words, you can still be smaller than a divergent and still diverge, but the comparison test won't show you. You'd have to switch to a different test. So being bigger than a divergent means that we just have to show that 1 over n is actually less than n plus 1 over n squared. Is this a true inequality? Well, if you're not quite sure, since they do not have matching numerators here, you could just cross multiply and see if this is still true. So if I cross multiply here, I'd have n squared is less than n times n plus 1, and it doesn't change the inequality, of course, because we're working with numbers that are positive, so maybe I haven't put that there, because we're starting at n is equal to 1. And then maybe one little step just to really set your mind at ease, that's n squared plus n. So I can see definitely that n squared is less than n squared plus n because we're starting at 1, so this is always going to be at least 1 bigger than this other side that's over here, right? At least 1, because we're starting at 1. So it is true. It is true. So we could use the direct comparison test. We just have to make sure that we write this thing up. And I would say something along the lines of f of 6 is equal to summation from n equals 1 to infinity of n plus 1 over n squared diverges since, let's say, 0 is less than 1 over n, which is less than n plus 1 over n squared, and our summation from n equals 1, I guess, to infinity of 1 over n is the divergent harmonic series. And you can point out that that is the p-series test where p is equal to 1, but making a connection to it being harmonic should be fine, and I might even just say by the direct comparison test. Okay, now on this one, remember I said that there was a second possibility that you could have done, which is the limit comparison test, which is the test that you would want to go to if you can't make this little inequality happen. If you can make it happen, then bam, you're done, right? Because that's all the requirement is for your comparison test. You have a divergence series, and then you're just showing that yours is bigger than the divergent series. So for the limit comparison test, if you were going to do that, so I'll just write this down here, limit comparison. Not that you have to do both, but I'm saying, hey, this is supposed to be a review video, so why not review it? You would go like this. Take the limit as n goes to infinity, and you're taking a ratio of these two things. It doesn't really matter which one's on top. So n plus 1 over n squared over 1 over n, and then multiplied by the reciprocal here. This is limit n goes to infinity. This n that's on the bottom is going to come up to the top, making that n squared plus n over n squared, which is equal to 1. So what it's basically saying is that our series and ratio, these things are getting closer and closer to being exactly the same thing, since the ratio here is 1. Sometimes it's equal to 2, so in other words, one of them is twice as bigger, twice as much as the other one. One of them could be a half, and in any of those cases, this test is saying that these both do the exact same thing. This is 1 times as big. This one is 1 times as big as this one, essentially. It is finite and positive, so this thing also diverges by the limit comparison test. Wow, what lovely writing. Make sure that your writing on the AP exam is just as clear as this, and if it's not, just do this. Just put a little lasso around this thing and then convert it to text, and yeah, notice that it would convert it to something that's complete garbage. What does it say? Diverses by 1 mit comparison test. Wow, it doesn't even have a little I in there. Yeah, okay, so make it maybe more legible than this. There's one other thing that you have to point out, and that's the thing that I pointed out here, is that whatever you're comparing it to also diverges if you were using the limit comparison test. Point-wise, what do I think this is? I think coming up with this guy is a point. So in other words, finding f of 6 as what that series is, and then the other one is the converge or diverge. So diverges here with your reason. Reason is definitely crucial here to get that point. And then let's look at B. It can be shown that f of negative 3 is equal to this business, which reduces to this other business right here. And the first three terms of this series sum to S of 3 is equal to negative 1 over 125 over 144, and show that, guess what this is? This is an error bound. And you have two choices when it comes to an error bound. One of them's easy, one of them is less easy. Guess what? This one is the easy one. This one is the alternating series error bound. How do I know that? Because we have an alternator in here. This is an alternator in disguise. This is essentially the same thing as, I'm going to highlight this guy. This is the same thing as negative 1 to the n times 1/2 to the n. So we do have this little alternator in here. Okay, so in order to use the alternating series bound, we do need to make a connection that this is bound to the first neglected term. And the first neglected term for us has got to be the fourth because we're using the third partial sum. So we look at the next term in line. So this is basically a sub 4. Okay, so let's see if we can find the fourth term. Now, the fourth term doesn't mean that we stick 4 in for x. There's no x's in here. What the third partial sum did is found, so s sub 3 is equal to a sub 1, because they stuck a 1 in here for the first term, plus a sub 2 plus a sub 3, right? And so this is the reason why we're finding the fourth term in order to bound this error with. So to find the fourth term, all we got to do is stick in a 4 for the n. So let's do that. So I'm going to say a sub, not n, 4 is equal to a 4 plus 1, negative 3 to the, no, I don't have to use that one. Why am I using that one? Use the simplified version anyway. Over 4 squared, negative 1/2 to the fourth. All right, now let's just kind of simplify all of this stuff. So this is going to be a 5 over 16. This is now a positive number because we're raising it to the fourth power, and 2 to the fourth. It's 2 times 2 is 4. 2 times 2 is another 4. 4 times 4 is 16. So times 1 over 16, which is 5 over 256. Okay. All right, so that's what our term is. Now we just have to make sure that we show our work here. So I am going to say, remember, in order to actually use this, your alternating series actually has to be a convergent alternating series. So I just got to point it out that it does. How do I know that it does? Well, look, this is f of negative 3. F of negative 3 is inside, where did I put it? I think I put it right up here. It's inside this interval of convergence, so I know it converges. So I just got to point out that the terms do what an alternating series are supposed to do, which is decrease in magnitude to 0. So I am going to say something along the lines of, since f of negative 3 is an alternating series whose terms, look at how clear this writing is. It's like this hybrid of cursive and print that's gorgeous with this Apple Pencil. Anyway, alternating series whose terms decrease in magnitude to 0. See, you can use the alternating series test to show that's true, but you know what? Like I just reasoned here, I know that it has to converge, and the only way that an alternating series converges is if the terms actually get smaller and smaller to 0. There you go. And this is the criteria that must be met in order for you to use the alternating series error bound. So let's see, since this is whose terms decreasing magnitude to 0, the alternating, maybe that should be a capital A. Yeah, because it's the title of something. Alternate series error bound. Whoa, that should be capital E also applies. And so what I'm going to do is just set up my little inequality here. So absolute value of f of -3 minus, what the heck was it? Oh, I can just write s of 3 here. So I guess since it's minus and it's a negative, actually it would be plus, but I don't care, is less than or equal to a sub 4, which is equal to, what was it, 5 over, where did my 6 go? Because that's 16 times 16 is 256. I'm pretty sure I wrote it. 256. You'd have to rewind the tape just to be sure. Yeah, but I have something to shoot for. They always do this. They always give us a kind of clue. Is this thing less than 1 over 50? I think it is. Just to be sure, though, let's cross multiply here. So I would have 5 times 50 is less than 256. This is 250 is less than 256. So yeah, that is absolutely true. All right, so that should do it. Okay, point-wise, obviously it's worth a point for your analysis here, showing your work using the alternating series error bound. And it might be another point too, and I think it is actually using this fourth term here. The first neglected term. Wow, this is just part B. There's more. Part C. Find the general term of the Maclaurin series for f prime, the derivative of f, and then find the radius of convergence. Oh, they just gave us a free question here. Radius of convergence, not the interval, but just the radius. The reason why it's free is because f prime has the exact same radius of convergence as f does. The only thing that changes is the interval, because you sometimes lose an endpoint when you're taking the derivative. So sometimes you won't have the exact same interval of convergence, even though the radius stays exactly the same. So if you just point that out, you don't have to do anything else, and bam, that's a free point right there. Okay, so I'm going to write f of x is equal to, this is just the original little series here from n is equal to 1 infinity, and n plus 1, x to the n over n squared 6 to the n. So remember that you can do calculus on this generalized term. The reason why you can is because this is essentially just a really long polynomial, and you're applying the power rule to the x terms, just like you would in this generalized term that's right here. Now, one of the things that usually happens, though, is that you lose the first term. Let's see if that's going to happen here when we take its derivative. So I'm just going to quickly plug in 1 and see what happens. So if I stick in a 1 here, that makes this 1 plus this, it gives me a 2 over, and here this would be a 1 squared, so that's just a 1, big deal. Oh yeah, so times 6 to the 1 times, and then we're plugging in, oh no, this is just x, so x to the 1 power. Yeah, clean this up. This is 6 over 2 over 6, which is just a third, so it's just x over 3, I believe, and then, so on. Okay, so when I take the derivative of this, the first term is going to be a third, so keep that in mind. So when I take its derivative, this guy is going to be a third. That'll help me figure out if, this changes or whatnot. Okay, so let's say f prime of x is equal to still a summation. We'll figure out if it starts at 1 or not. But whenever we take its derivative, these n's are not affected. What's affected is only this x, because that's what you're taking the derivative with respect to. So you're going to leapfrog that n down, and you'll have n times n plus 1, x to the n minus 1 over, and then everything else stays the same, n squared, 6 to the n. And does anything simplify? It doesn't look like it. Okay, so here then let's just check to see if we get 1/3 if we just stick in the number 1 like we did over here. So if I stick in 1, I'd have 1 times 1 plus 1 is 2, x to the, this will be a 1 minus 1, so 0 power over 1 squared times 6 to the 1 power. And let's, of course, that's 1. 2 over 6 is going to be 1/3. So yeah, that's 1/3, which is the first term that we expected it to be. So 1/3 plus blah, 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 blah. So this does start at n is equal to 1 to infinity. All right, so I do believe that we just found f prime of x. Oh, great. And now we just need to find the radius of convergence. So if they hadn't given us the radius of convergence of f, what you would have to do is use the ratio test, of course. But I can completely avoid that for the reasons that I previously stated, which I will not restate because I am running out of breath. So I am just going to say, since f of x has a radius of convergence of 6, f prime of x also has a radius of convergence. I think it's a missed opportunity. We should just abbreviate this as ROC. Radius of convergence it has a ROC of 6. Convergence of 6. All right, I think that's a 2-pointer. So a point for this guy, boop, boop, point plus 1 here, and then a point for your radius of convergence, however it is that you find it, whether you use the ratio test or not. We have one more section. We just need the endurance to get through it, especially since, of course, when you're actually taking this exam, this is the last thing that you guys are going to be doing. You're going to be exhausted. You can do it. Watch. Let g of x equal, they give us another little series here. Use the ratio test. They tell us to use the ratio test to determine the radius of convergence of g of x. Okay, this Maclaurin series. All right, so we are forced to use the ratio test. Luckily, the ratio test is super easy to use, and it just goes like this. We take a limit as n goes to infinity. I bet that is important, looking for that notation. And since we have a quotient, what I'll do is I will multiply by the reciprocal. And remember, what we're always doing is a sub n plus 1 over a sub n does have to be a absolute value. And so you're basically comparing a series to itself to see what happens as you get further and further and further away from 0. Is the common ratio between those terms approaching some finite number. And if that finite number is less than 1, just like a geometric series, then we know it converges, right? Okay, that's what we're checking. So absolute value of, everywhere there's an n, we're going to add 1 to it. So this is going to be n plus 1 plus 1, which is n plus 2. X to the, be careful here because this is not 2n plus 1. It is 2 parentheses n plus 1, which is going to make it a 2n plus 2, over n plus 1 squared, 3 to the n plus 1 times, and now multiply by the reciprocal here, which is n squared, 3 to the n over n plus 1, and then x to the 2n. And then go ahead and get out your cancellation crayon because stuff always cancellates. Real word. So the 3's, for example, go away. Subtract those exponents. You're left with a 3 on the bottom. And let's see, this new exponent here is going to be 2n plus 2. And when we divide it by x to the 2n, that part will subtract away, leaving us with an x squared. That's a squared. And then none of the other stuff cancels, unfortunately. So just let's simplify here. So limit n goes to infinity. Let's see if we still need absolute value here. All the n's are positive, so none of that needs absolute value. And x squared's positive, so we don't need absolute value around that. And then 3 obviously is 2, so it's gone. Let's just list stuff out. So n squared times n plus 2 on the top over it's going to be n plus 1 cubed. So n plus 1 cubed times x cubed over 3, I believe. So all of this, using some pre-cal rules, you have an n cubed up top, because n squared times n cubed here. This is also an n cubed. So this is all 1 when we take the limit, and the limit does not affect the x stuff. So this is just strictly equal to x cubed over 3. If this is going to converge by the ratio test, that common ratio must be less cubed. Was that cubed? It was not cubed, was it? It was squared. Okay, well, I caught the mistake. Shoo! All right, that is got to be less than 1. Multiply the 3 over, and we just found ourselves the radius of convergence, I think. So this means that x squared actually didn't, because this is x squared, and we still have to take the square root. So in terms of like a quadratic equation, getting rid of the absolute value, you would have to take the square root of this thing, and so x would be equal to the square root of 3. It's actually plus or minus, and your interval of convergence would be negative square root of 3 is less than x, which is less than positive 3. And if they were actually asking for the interval of convergence, they're not, but if they were, then you would have to test out these endpoints to see if they also worked. Anyway, but they're not. They're just asking us for the radius of convergence, and I just might formally state this. So by the ratio test, maybe even say that. So by the ratio test, the radius of convergence for, what the heck is this called, g of x, is the square root of 3. What a weird radius. Okay, let's see how many points that we have left. So I thought this was 2, 3, 4, 5, 6. We got 3 points to spend. So how are we going to spend them? Let's see. Obviously, conclusion, the radius here is worth a point. And it looks like it should only be 1 point, like using the ratio test. So where's this mystery other point come from? Maybe they just said that this is worth 2 points or something like that, using the ratio test. I don't know. Well, here, let's check it out and see what they did. Okay, so for part A, it was worth 2 points. And it says, consider this thing. I think that's what happened whenever we just plugged x is equal to 6 in there. And I think that, no, actually, I thought this is what our point was. But notice that it says that it's equal, so we could get a point from there. And answer with reasoning, and it says, hey, because this is greater than 1 over n for uh-oh, I don't think that I included this part in here for n greater than or equal to 1. I may not have gotten this point here. In the harmonic series, 1 over n diverges. Notice they did that. They did exactly what we did, is that they didn't apply a test to this. They just said, hey, this is the harmonic series which diverges, and said that this also diverges by the comparison test. Oh, gosh. Did we just make a crucial error here? Let's see. It's right here is where we should have inserted this. Oh, man. 4 n greater than or equal to 1. Okay, anyway, let's see what notes that they have, because maybe they mentioned that. I don't know. All right, so some scoring notes to earn the first point. Using either the comparison or the limit comparison test, a response must consider this term, which can also be shown by considering this one. And this is the one that was really the important one, I think, because that's what it reduced to. A little easier if you just go ahead and you cancel out your exponential terms. And to earn the second point using the comparison test, a response must demonstrate the terms blah, blah, blah are larger than the terms of the divergence series, blah, blah, blah. This earns both points. Uh-oh, so maybe we would get it, because look, it says this is greater than that diverges, earns both points. Okay. I might be safe there with that extra point there. All right, so response does not need to use the term comparison test, but the response cannot declare use of an incorrect test. And then it gives us an alternate solution using the limit comparison test, which I said, of course, was the second one that you could do. And they did the same thing that we did, taking the limit of the ratio and saw that it was 1. And to earn the second point using the limit comparison test, response must correctly write the limit of the ratio of the terms and show that it's 1 for that divergent series. The response does not have to drop the name limit comparison test, but if they do drop the name of something, it does have to be the correct one. Okay, part B, it was worth 2 points. Uses the fourth term. So this is the one where we were supposed to use the alternating series thing, and then our verification was the second point. So let's see what they said. So f of -3 is equal to blah, 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 is an alternating series with terms that decrease in magnitude to 0. Those magic words, they are ringing in my ears because we did say that. And then by the alternating series, error bounds, this thing is equal to that, approximates f of -3 with error of at most, and they use that next term here. So uses the fourth term, which was less than, oh, this is an interesting way to write it. They just basically scaled this one up to have the same numerator, so multiply the top and the bottom by 5, and then we can see with the bigger denominator, this fraction has to be smaller. Okay, there you go. So, scoring notes wise, first point is earned for correctly using x is equal to -3 in the fourth term. Listing the fourth term as part of a polynomial is not sufficient. It has to be actually simplified, I guess. Using x is equal to -3 in any term of degree 5 or higher does not earn this point, obviously. You got to use the fourth one. Obviously, the expression blah, blah, blah earns the first point, but just 5 over 256 does not. In other words, they have to see a connection between your actual simplified answer and the work that it took to get it. I'm pretty sure that we had that. I'll double check that just to make sure. Are we still on B? Yeah, we're just on B. Yeah, it's right there. It's pretty clear. It is pretty clear. We already talked about that. And to earn the second point, the response must state that the series for f of -3 is, oh god, I think this is important, is alternating, or that the alternating series bound is being used. So you do have to say that it's alternating. It is unclear whether or not you have to say that it's like fits the criteria as this part, alternating series with terms that decrease in magnitude to 0. I think that is kind of key, and I would make sure that I put that as part of my response. The response of just blah, blah, blah is less than 1 over 50 earns both points, provided it is accompanied by the indication that the series is alternating. So there you go. And a response that declares that the error is equal to 5 over 256 does not earn the second point. Remember, it's got to be less than. Okay. Part C, 2 points here. The general term, which is the thing that we reduced ours to after did we reduce? Yeah. So it would take either one of these. It has an equal sign. It will take either one of those. and then the radius, and let's see what they say, because the radius of convergence of Maclaurin series for f is 6, the radius of convergence of f prime is also 6. Yes, that's what we said, so we got that point too. A response of this guy earns the first point. Any expression mathematically equivalent to this also earns the first point. Why do they have to restate that? That's exactly what they just said there. Response need not simplify this, but any percentage simplification has to be correct. Second point is earned only for a supported answer of 6. The second point can be earned without the first. So even if you miss this, if you still knew that the radius of convergence is still the same when you take the derivative, you could still get that point. Alternate solution for the second point is actually using the ratio test, of course, or the root test. You know what I'm going to do? That's what I'm going to do. Ratio test, of course, because we practiced that. Root test, we left it on the cutting room floor. All right, finally D. Let's take a look. This video is getting long enough as it is. It has, it is the 3 points, and let's see how they set it up. So sets up the ratio. Just setting up the ratio correctly is worth a point, and then actually taking the limit of that is worth the next point, and having a radius of convergence of the square root of 3 is the final point. Scoring notes. The first point is earned by presenting a correct ratio with or without absolute values. Interesting. Once earned, this point cannot be lost. Any errors in simplification or evaluation limit will not earn the second point. First point is earned for all of these kind of ratios. I'm not going through all those. Or these, geez, responses including the symbol can earn the second point for using limit notation to correctly find a limit of the absolute value of the ratios to be this guy. Such responses earn the third point only for a final answer of the square root of 3 with a valid explanation for the reporting of the reciprocal of 1 over the square root of 3 to earn, because of course we had to multiply that square root of 3 over, right, this guy. After taking the square, we actually had to multiply the 3 over and then take the square root of that guy. Okay. To earn the second point, a response must use the ratio and correctly evaluate the limit of ratios using correct limit notation. So don't go be lazy and not put your limit there. And the third point is earned only for an answer of the square root of 3 with supporting work. Et voila, here is the final question on those free response questions series. It should be a lot of fun, guys.